I just thought I'd mention just a few things before we start looking at other people's data. The first one is Alonso just told me that some people might be interested in using MRView for looking at fMRI data. I just thought I'd highlight the overlay tool, which you can use to look at things like that. So here, for example, I've got an overlay of an FA map, and I can apply a threshold at some value. Hang on, that doesn't work at all. Hello. Hang on, there we go. That would be better with this. No, that doesn't work today. Sorry, the threshold's being applied to the wrong image. There we go. And you can obviously make your overlays transparent, but if you apply a threshold, then you can obviously figure out, if it's a t-value map, you can figure out exactly where you want your thing to have, and you can have multiple overlays simultaneously, and each one can be made independently transparent. And if you want, if I remember this, you can actually modify the opacity of both at the same time if you do that. Anyway, there's lots of different ways of doing that to look at this kind of data, and you have a color bar for each of the overlays independently here. And again, if you just press the space bar, you can hide everything. But you can also, didn't say, is you've got control of all the independent bits of the display here, so I can hide various aspects of the thing. I didn't also mention the little markers that you have here, AP, left, right. These will track when you start rotating things, so you can tell where you are in space, whether your brain goes funny, which is quite important. Otherwise, you forget where you are. But anyway, so there we go. So if you were interested in using these MRView for other applications, it's entirely compatible. It's designed to be a generic, multi-purpose, whatever, and then the tools is where we add functionality that is domain specific, but it's much more general than that. All right, so that's just one thing. Another question I had was, what kind of computer should you get if you want to start using MRtrix for applications? So there's several levels. The first one is obviously bigger is always better. If you get a good CPU with lots of cores, then MRtrix will use all of them. I've got a 6-core CPU with hyperthreading, and that flies through stuff. It's great. The second consideration is RAM. You will need RAM to compile MRtrix in the beginning. It's quite demanding on that, but there are ways to get around some of these issues. But I reckon 4 gig is probably your minimum. If you want to look at HCP data, you're immediately looking at least 8 gig, if not more, maybe 16. And the reason for that is not because MRtrix is particularly memory hungry, it's because the HCP dataset itself, if you uncompress one of those datasets, it's 4 gig. So if you want to do even just, the slightest thing there, it requires at least double that size to do anything sensible with it. So I recommend you have a lot of RAM. Everything else is kind of what you want, apart from the graphics. So if you want to be able to run MRView, especially the volume render thing, which is quite demanding on the hardware, you need a decent graphics card with good OpenGL 3.3 support. There's a lot of considerations there, and I could talk about it all day. The first thing is, if you're running on Linux, the biggest problem is not so much the hardware, it's the software. Your drivers need to be up to date to run OpenGL 3.3. I'm running the open source drivers here, not the NVIDIA ones, but that's because they're sufficiently up to date now. But that's only been the case for about a year, so they need to be very, very up to date. But if you run the NVIDIA drivers, then there's no problem. If you run an ATI card, the drivers are quite picky, and certain things I haven't figured out why they're not working yet, but it's only for the volume render that it's a problem.
Do you recommend any platform? Say, if you don't want to get in trouble, I recommend Linux, I recommend Windows, I don't know.
I will always recommend Linux. But I realize that it's not everybody's cup of tea. So it runs just fine on the other platforms. Windows has a few more glitches in there, but they're not. They're just mostly about compiling the software more than anything else. Once you get over that, things seem to work pretty well. Remarkably, I was a bit surprised, but there's this thing on Windows called MSys2, which tries to be like a Unix environment on Windows, and that's really helpful to get things going, but it can be fiddly to set up. Once it's set up, though, it works just as fine. So I've got it running on my little Windows netbook. It's a really, really crap little laptop. It took 4 hours to compile MRtrix, but it ran. So that's fine. A lot of people use it on Macs, no problem. But yeah, so on the graphics card front, and especially for Linux, I'd recommend NVIDIA. ATI is normally fine as well. If you get an NVIDIA card and you want to not spend an enormous amount of money, do not get the Quadro range. That's the workstation grade cards. They're, for the money, terrible performance, but they're designed for 24/7 operation, which is why they're more expensive. But if you go for the gaming cards, so the GeForce range, it's all good. So I've got something that didn't cost me too much, and it's got like 2,500 cores on it, and it just flies through this stuff. It's great. So that's my recommendation. So if you for the hardware, I typically on Linux would recommend NVIDIA, but ATI is catching up on the driver as well. So there's not much in it. If you want to run ATI, it's fine too. Okay, now coming back to the general hardware. So that's just a minimum to get MRtrix running and to do general processing. If you're interested in doing the pixel-based analysis stuff, the problem with pixel-based analysis is that we have to compute a matrix of pixel-to-pixel connectivity. There's a lot of pixels in the brain. That's a massive, giant matrix. It is sparse. We try and keep it sparse, but it's still an enormous amount of information. And if you follow the recommendations on the documentation site, you'll find that Dave Raffelt, who's the main developer on this, recommends upsampling your data by a factor of 2, so you get 8 times the number of pixels. It can take 100 gig of RAM. Okay, so if you're serious about doing pixel-based analysis, do go for a lot of RAM. A lot. And that does dictate what kind of computer you can get. I mean, not every motherboard can take that much RAM. So anyway, so that's that on the hardware. So there we go.
One last question about the viewer.
Yep.
Surfaces? Can you load surfaces?
Now we can.
Now you can.
Hang on. This is very fresh stuff, so I haven't looked at it. But in the Connectome tool, you'd have to talk to Rob about this. But he's got facilities now to start looking at using surfaces, and there's a lot of movement on that area. So it's not mainstream yet, but it will be coming. So before I start looking at data, there's a couple of things I'd like to talk about, which are very routine issues that you come up with when you do diffusion analysis. That kind of make quite a big difference. So strides is something that can fox a few people. We get confused about it every so often as well. But it is quite important to get your head around it. This is not to do with diffusion specifically, but it is quite useful. In MRtrix 3, I've started using the word strides to refer to how the data are stored on file. The problem is on file you have one big long array of bytes. It's a linear array, and yet you're talking about a 3D, 4D, maybe 5D image. So you have to have some way of mapping a given voxel in 3, 4, 5D space to a given location on your linear array of bytes. And the way we do this is we talk about strides. And the strides is basically telling you how many voxels do I have to skip, or how many intensity values do I have to skip to go 1 voxel to the left, for example. So typically that would be a stride 1. It means the value next door to you on the file is next door to you in the x-axis. And then maybe the y stride would be 128 if your image is 128 wide. And that means I have to look 128 values further along to find the next value along the y-axis. And then the z stride might be 128 times 128 to tell you where you look at these things. So this is generally how it works. And Nifty uses this particular, and MRtrix uses this particular coordinate system. So X is increasing from left to right, Y posterior to interior, and Z inferior to superior. Now, MRtrix, the MIF format that I have, is completely agnostic to that. You can do whatever strides you want. You can do volume contiguous. You can do Z contiguous. You know, all kinds of strides, and it gets really messy to worry about it. So, for example, when you specify strides in MRtrix, I can say I want strides 1, 2, 3, which means basically I want the x-axis to be contiguous, the y-axis to be the next thing along, and the to be the z-axis to be the next stride along. And it will figure out that that actually means 1, then the x dimension, then the x dimension in terms of 1 dimension. That's the strides that you would get when you specify that as the strides. So it is very flexible. So for example, I could put the last axis as 1 here, and I could put 2, 3, 4, 1, and that would be volume contiguous storage. That's useful for processing, high performance processing, when you want to keep everything together. You know, you process a voxel all as one chunk of data. If it's all there in the RAM, it's very easy for this hardware to optimize access to it. Now, Nifty also allows you to kind of have relatively arbitrary strides, but it does it in a different way. It does it by modifying the transformation matrix. So it's always going to be X, Y, Z as the strides, but then if your axes actually are rotated 90 degrees, well, your X is your Y-axis and your Z is your whatever axis, and it gets really messy. So MRtrix tries to fix that up for you. So if you go to a sagittal acquisition, for example, is often stored with a massive rotation to the data. So you get stacks of images that are actually stored as if they were axial, but actually they're sagittal slices. And the transformation matrix tells you that actually your x-axis in this data set is actually the y-axis or something, and so on and so forth. So MRtrix tries to sort all that out for you, so you get presented with an image that is more or less x is left-right, y is anterior-posterior, z is inferior-superior. But it can get quite messy. And the reason it can get quite messy is because if you start, this is basically what I've just said. It gets messy because if you start using different packages that don't make the same kind of assumptions about, or don't read the data in the same way, you can get some really weird problems coming up. So one classic example for that was top-up and eddy. And FSL view still is a problem. So for example, if this used to be a problem, you take a Nifty image produced by some other package, convert it, process it using MRtrix, and it eventually ends up with different strides than the original, even though it's exactly the same information. It's just that we've modified the transformation matrix to match, and it's all self-consistent. But then you feed that and trying to overlay an FSL view with the original image, which is different strides, and it's all back to front and upside down. And people used to complain about that a lot. Whereas in MR view, it all was fine because it was all internally self-consistent. The other one that we had was top-up and eddy. So sometimes previous versions of eddy would kill the transformation matrix altogether. Just get rid of it. So if your data was standard DICOM, it would typically have the axes right to left, not left to right, and anterior to posterior, not posterior to anterior. So it was rotated 180 degrees. And then you try and pass that to eddy, which would take account of the transformation matrix in the data that you had, but the output of top-up was basically flipped upside down. Then you were applying the wrong field map to your data. I lost a lot of hours trying to fix that and figure out what was the problem. So MRconvert and a lot of other commands have an option called stride, which allows you to manipulate the stride of the output data set. And you can tell it exactly how you want your data to be laid out so that everything is fine. But generally, if you use MRtrix only, you never have to worry about it because we typically take care of these things. Commands that output data where it's important to have it in a certain layout will do so. So for example, DWI to FOD will use volume contiguous storage for the output if it can. So with the MIF format it can't with Nifty, unfortunately. And that's useful because then the tractography runs faster. Because every time it needs to kind of figure out where to go, it has to have the data for that voxel. And if it's all together, it's easy to just load it into the CPU and operate on it. And what you'll often find, for example, is some commands will, when they run, if the data are not in the right strides, they'll preload the data. And that's basically to fix up those strides because things run just so much faster. So it just loads it up in RAM in the right order so that it's then faster to process later on. Anyway, that's quite technical stuff, but it is worth kind of keeping in mind because it does influence, you can come up against problems with it. The gradient table in diffusion is a major source of headache. So the gradient table is the b-values and the directions for each volume. It's pretty critical to get it right. But there's a lot of conventions as to how these things can be stored. So the direction vectors themselves, the coefficients, the 3x, y, z, can be relative to the scanner axes. It can be relative to the nifty standard coordinate system. It can be relative to the axes of the images themselves. So if you tilt your axes, your image, so it's an oblique acquisition, then your vectors, your coordinate systems are different from the scanner, and you will get different interpretations of the vectors depending on which one of these is actually the right convention. And that makes it spectacularly easy for things to go sideways. On top of that, you have the issue that bvex and bvals are relative to the image axes, and they're separate files. I find that very scary because they should really be stored in the image itself, which is what MIF allows you to do. The whole gradient table will be there if it can find it. So one issue, for example, is if you convert your image to nifty, you get your bvex, bvals, everything's fine, but then you decide to regrade your DWI to match for example, your T1. At that point, the image axes might be different because the T1 might have a different orientation, and what do you know? Your bvex and bvals are no longer consistent. You'll have different orientations as a consequence. Just as a little word of something here, so if you use, I always recommend to people to go back to the DICOM data if they can and stick everything in MRtrix because, especially the MIF format, because all this information gets stored in there. So if I look at my DICOM data here, this is pure straight off the scanner. I look at the diffusion weighted image dataset, which is number 7. Check it out. The last one here, DW scheme. It's a pretty big file, but I've got 167 entries in my gradient table. If I want to find out what these are, I can stick another option here to tell me, and here it is. That's the entire table, X, Y, Z, B value. Okay. And if I then convert the image to some format, MIF, sorry. So let's call it data.mif. Put it in there. Dang. It's the old mosaic format from Siemens, which is really good fun. If I look at that image itself, DW scheme is there. Okay, so it's always there with the data, with the image. You can't lose it. You can't apply it to the wrong image. It's there, and I think that's a really important thing to have. So, just to have a look at exactly what can happen, I've got these graphics, and it's all kind of quite difficult to deal with. But when you convert your image from DICOM, the image is in the. I'm not going to do this. I'm not going to go through this. But anyway, the point is, this is basically saying what I was saying. That if you regrid your DWI to a different orientation, the bvex and bvals can be completely corrupt. If you then have to deal with DICOM data, things can get really, really good fun. We try and take care of all of this for you. But for example, on the Siemens scanner, the gradient directions will be stored relative to the DICOM standard coordinate system, which is nifty, but X is reversed and Y is reversed. On a Philips, it is standard coordinate system, so DICOM standard coordinate system, if the overplus option is used. Actually, no, it's always DICOM standard coordinate system. It's more about what you specified. I'll talk about that in a minute. On a GE system, until recently anyway, it used to be stored with respect to the image axes. So on an oblique scan, again, in the DICOM, the values themselves will be stored in a different coordinate system than on a Siemens or a Philips. On top of that, on a Philips, if you specify your gradient directions manually, if you take the overplus option, then they're specified with respect to scanner coordinates. But if you take tick that off, then they're specified with respect to the image axes. So there's all kinds of ways for things to go very, very wrong if you don't keep, keep track of all these things. One thing you can do is acquire some test data with a really strong angulation and then no angulation and verify that actually the directions that you get are correct, because it's so easy for things to go very badly wrong. So there we go. I think I've said it. Yeah, the point here is a lot of effort has gone into ensuring correct import from DICOM. Use it. Okay. Something else about the quality of the gradient table. Yeah, sometimes some of the acquisitions that you might be using can have badly distributed gradients. If you see something like this, for example, you've got a diffusion weighted image that's got, let's say, 60 directions. You think I can use LMAX 8, no problem. You start to run DWT response, for example, and it tells you that they're poorly distributed for LMAX 8, and your condition number is horrendous. You want this to be close to 1. This is bad. It means that you've got about 1,000-fold noise amplification in your spherical harmonic transform. Not good. So it reduces the LMAX for you, and sometimes it reduces it really a long way down. So the Philips Overplus data sets will have that problem every time, guaranteed. It's a terrible option, never use it. If you have a Siemens scanner and you have the MGH works in progress package from way back, that is also terrible. It was not optimized very well. If you have an older GE or the data from an old GE, those directions are also optimized pretty badly initially. They fixed that a few years ago. So these are things that you might be think about. Anyway, there we go. I think that's enough for now. So now, unless there's any more questions, we're going to have some fun with other people's data and see what we can see. Okay? Right, cool. All right, so I've got a few data sets. So let's start with Eduardo here. I have not looked at this before, so we shall see what we see. So these have been pre-processed with Eddie. Let's find out.
I have one question. It's very basic. How do you change fast image volumes in your MRV?
Right arrow.
White arrow?
Right. Left and right.
I can't. My computer.
You can't?
I can't see my computer.
Oh, we'll have a look at that then. That's not right. Otherwise, next volume, that's
No, I have a very
pretty
thing. No, but it's okay.
Okay. Anyway, so the first thing I would do is just inspect the data manually. So take off interpolation. Again, interpolation is, where is it? It's probably here. Yeah, I for interpolation, take it off. It's probably cleaner to look at it that way. Let's have a look at it. So there's 2 B values in there, and that's the B3000 data. There's a lot of noise in there. That's fine. But it's all nicely co-registered, so we can just keep going. So let's get a mask out of these data. So if I run this is a nifty image. If I run that, it'll probably fall over as soon as it tries to get the gradient table. Yep. If you have nifty data with BVEX BVALs, you can specify the gradient table. So, hang on, what have we got here? DTI, geez, BVEC. I'm going to do something funny here. There we go. So that should do it. BVEC, BVAL, yeah. Okay. So this is a bash construct. Basically, it expands to both the BVEC and the BVAL as separate arguments. This is actually what it does. Okay. This is a command I should have written to not confuse everybody to bugger you, but anyway. So at that point, I have a mask. Let's just inspect the mask and make sure it's kind of okay. It's not too bad. And I want to get a response from this. I'm going to use just a single shell, outer shell response from that. So let's just copy paste this stuff so I just have it. Let's go for it. So let's hope it doesn't take too long. The fan on my laptop has just kicked in, so clearly it's doing something. So while that's going on, I might inspect the other data set that I have and see what happens with that one. Oops. So let's have a look at that one. And poof. So it's a reduced field of view, and there's a bit of eddy current going on. So you can see there's a bit of eddy current motion going on in the data here by looking at the motion of the interface here. That's not unexpected. It's a Philips system, I'm guessing. Is that Philips system? Which uses a single pulse gradient spin echo rather than the twice refocused one. Have you got multiple b-values in that one?
That's 2 b-values.
Okay. One thing that's quite useful if you want to have a look at you figure out what's in your data. If it was a MIF file with a diffusion gradient table in it, you wouldn't need to pass the BVEX bvals information in it. But I will bval. So MR info, and you can ask it how many shells have you got, and how many direction per shell. So I know I've got 2 B0s, 32 B1000, and 32 B2000s. This is zipping through it, that's fine. I'm not going to run anything more because that will probably kill my laptop. By the way, in terms of those people asking about the hardware requirements, this is my memory consumption, the green stuff here, the dark green stuff. This is an 8 gig system, so it's not using a massive amount of RAM. CPU-wise, yes, it's going hell for leather, but that's a dual core, no hyper-threading, so it's just running 2 threads. I think any modern laptop would do better than that nowadays. How many iterations has he put in? Jeez. Anybody else have any questions or any comments or anything that we want to talk about while this is going on? Oh, it's actually done something. Sorry, I'll just inspect the response. So have a look at the response and find out what it looks like. This is B3000 data, sorry. This is exactly what I'd expect to see, so that's encouraging. And now we are in a position to run the CSD. So I'm going to do a straight CSD. What that will do is use just the outer shell. It's just because otherwise it will take too long to run on these data. So again, I'm just going to go and copy paste the whole bit that was there. And there we go. I want to use a mask that I set earlier because that makes things a bit quicker to process, and go for it. I've got to tell it the response. Off we go. So you'll notice that warning here. It's detected it's a multi-shell sequence, or at least that there's, not a single b-value in there, so it's selected that b-value here.
It always selects the big one.
The outer shell, yes. You can tell it which shell if you want to. Just have the option minus shell, the number, not the index, the actual value that you want. So I could put minus shell equals minus shell 1000 and get the b 1000. If you're bored, you can actually have a look at the output. Oh no, you can't these days, it's done differently. Oh no, we might be able to. I'm just trying to think if that will work. Yes, it will. You can actually see it on the fly, filling itself up. This is the beauty of memory mapping for those geeks in the audience. You can see it actually happening. So let's have a look at the FOD image. So very much what you expect. It's all fine. Let's have a look at the ODF display. Yep. The classics, that's fine. So it's a bit, a bit noisy, I guess, but not unexpected at B3000. But it's not too bad. So let's do some tracking while we're at it. Any particular tracks people want to see? No?
The optic nerves.
Optic nerves? Oh no. Have you distortion corrected these data?
I think we're not there because of that. I think there's going to be any optic.
Yeah. It's going to be tricky to see the optic nerve. I can see the optic radiations, but not the optic nerves. I mean, they're going to be blitzed by the distortions down here. I heard someone say fornix, so we'll go for fornix. Where are you? Jesus. Okay. There we go. So what I might do is just seed from here and see what I get. So just note down the position of that thing. So it's roughly 0, 18, 57. Let's put that in the background. Track gen on the FOD minus seed sphere. And I forgot what I said. 0, 18, 57. I'm going to have a 2 millimeter sphere, and I'm going to tell it to start tracking in the inferior superior direction roughly, and then we're going to call it fornix.tck and see what happens.
What was that last option you need to do?
Initial direction of tracking. So that just helps it make sure it starts roughly inferior superior. So let's kill that and have a look at the tractography output. So here you go. If you want to have a look at it that way, you can. But generally, you'll want to see where you are. So this is. So I'm not unimpressed by this actually. For a first go, it's not bad. You've got a bit of corpus callosum that went in there as well, so you might want to clean that up. And we can also have a look in this view as well. There we go. Let's just invert that. So there we go. That's quite a nice fornix. And you can, also display that if you want as, let's go full screen, using the lightbox mode to see it at different levels. If that helps, crop to slab, there we go. In various orientations. Okay, so that's that. And if I wanted to then go and clean up my data, because I've got these bits of corpus callosum here. So this is a bit unusual to see it that badly, but the simplest thing to do is just to say I'm only interested in stuff that goes around to the hippocampal formation. So let's say I just want the left side here. I'll take note of this -28, -7, 42, and I'll just tell it to include stuff. -28, 28, -7. 42, and I'll put a 10 millimeter sphere radius on that one, and that will fail because my file already exists. MRtrix is full of little safeguards like this to prevent you from accidentally shooting yourself in the foot. And that saved my behind quite a few times. So you'll notice here that it's working a lot harder to get these tracks, because out of the 4,000 generated so far, only about 150 actually make it to the target region. So I hope I've specified that region correctly. And we'll see.
The memory mapping work for the TCK?
Because it's a variable size file. That, and because the tracking buffers the output to write a bulk bunch of data in one go.
Version 2 used to.
Yes, it used to. It was actually quite hard to get it to work, to prevent bus errors particularly. But we've talked about doing it in this version, but it's, yeah.
So when you force a file that is already loaded, it's essentially left one on RAM, so you can
You have to,
compare it.
yeah, you have to kill it and then start again. This is on the issue tracker. You know, if you want to see, it's one of those things that we'd like to fix eventually, but we haven't got the time really, basically. So if anybody wants to help out, what we'd need to do is detect when the file has changed and then load the tracks that have been added since the last read, which isn't impossible. It's just that, you know. So for example, here that's not updated. I'll have to go and reload them. But there we go. Now I've got just that side of the fornix coming out, and the optic radiation. How nice. So yeah, this is probabilistic tracking. So of course you're going to get things that don't necessarily match with what you'd like, but by and large, it's not a bad way to do it. I notice there's a lot of various slice-to-slice intensity variations. I think that's the recon. Is that? Anyway, doesn't matter. Does anybody else want to try some of the different tracks while we're at it? RQ it, something? Sorry? RQ it? Okay, off we go. So assuming this is a normal right-handed person, we're going to track the RQ it on the left, so there, somewhere around here. And again, this is an example of where that initial direction of tracking thing is really quite useful, so I'm going to assume that it's going to be somewhere around here. To verify that, I'm going to load up the ODF display again and just verify that we're in the right region, so roughly here. Okay, so we're doing a sphere again, so 32 minus 2, 75. I'm going to use a 5 mil sphere. Initial direction of tracking will be in the y direction, anterior posterior, and I'm going to call that rqit.tck. I've spelt it wrong, I apologize. So let's kill that. Oh, that's not what I wanted. By the way, if you can have all these tracks loaded up simultaneously, it's not a problem. And you can display them all, and you can change their color so that you can see them as separate things, and that works better with lighting on if you want to. But I quite like color by track directions. So this is a very rough and ready SLF, basically, initially tracking from basically where the cursor is in the inferior superior direction. If we want the arcuate, hang on, let me just crop the slab again. Okay, so we'll be wanting those tracks that project roughly here. So probably simplest to look at those. So all we'll have to do is put an inclusion region over here. So 32 minus 27, 56. Ah. It could be easier to manipulate, but here we go. And I'll force that. There's another feature of MRtrix command which I haven't mentioned, is that option names don't need to be complete, they just need to be sufficient to identify the option. And what I mean by that is I could probably put -inc instead of include, and as long as there's nothing else that starts with -inc, it'll just use it. If you can't be...
I have a question. Could you go over the different algorithms in that command?
In TrackGen? Oh my god. Briefly. Hang on, let's just display what I have and then I'll go through the algorithms. And so there we go. I've got a bit of striatal fibers as well, but hey, I don't know. That's probably because, yeah, they come from there. So, there we go. Inarcuate. And that's, let's try and kill my laptop. Go for it. There we go. I'll invert that one so it can look at the other side. There we go. Bit too much. So this is where the interactivity on my laptop is going to grind to a halt, but you can see that it still behaves. So you can render your thing in whatever you want. Cool. Okay, there we go. All right. So the question about the different algorithms. So CCKGen does include quite a few. Algorithm here, you can specify which one. You've got fact, ifod1, ifod2, null-doost 1, 2, SD stream, and all sorts of other weird stuff. Fact is the standard 1999 tensor tracking. It means that you have to give as your source data, not the FODs, but the DWI data directly. And that does no interpolation on the input data. Tensor det is a deterministic tensor tracking that does trilinear interpolation on the inputs as well. Then you got a probabilistic tensor tracking algorithm which uses a wild bootstrap algorithm that Derek Jones proposed a while back. ifod1 is essentially what it was in MRtrix 2. ifod2 is the new stuff. Null-dist 1 and 2 are trying to use Jeff Parker's approach at doing the tracking without any information about orientation whatsoever, just to see what would happen if your data was non-informative, and you can try and build a null distribution for your tracks that way. I don't think I've never used it. I don't know if anybody else has ever used it. SD stream is using deterministic streamlines on the FODs or whatever things you have, as long as they're in spherical harmonics. Seed test, I think, is a way of outputting the seed positions or something. I can't remember, but it's probably not one that you'd ever want to use. It's just for interest. Does that answer the question? Okay. So anyway, so we've got a couple of tracks here. Let's try someone else's data, unless people want to do something else with it.
Monkey data.
Bring on the monkey data. Okay. Well, we'll just look at this other data first, and then I'll. But let's put it on while we're talking.
Monkey data.
How big is it? It's okay. Yeah.
This and this.
Oh, it's more than I need. Oh, it's
Yeah.
already copied anyway. It's fine. Yeah. All right. There we go. Off we go. So, well, let's look at monkey because it's fun. I have no idea what I'm going to look at. So. Okay, so this is fairly classic Phillips data. You can see that there's the reconstruction is masked out the outside, and that's to help boost the SNR inside. it can be a problem for getting a mask from the images. And I think the FSL can struggle with it as well as MRtrix sometimes. But otherwise, it's all fine. There's several B values in there, I think. And I'm guessing this is sedated or something because it's not moving at all. Perfect. Beautiful. So let's have a look at what we have in terms of the gradient directions and everything else. So what I've got is the BVEC and the BVAL. What happened here? Am I looking at the wrong place? Oh, sorry, yeah, okay. Oh, this is already in MRtrix format. Okay, fine. So you can also provide your gradients in MRtrix format, and at that point, that has to be in the scanner coordinates, not the image coordinates. So the BVEX is with respect to the image. The single file format, the MRtrix format, is with respect to the scanner axes. So I've got 330 entries in this thing with 2 shells and quite a lot of images at the B2000 range. Looks good. So let's get a mask for the data. I'm not sure how well that will work, but if I don't get one, it doesn't really matter. Sorry. Okay. So this is where we find out if the mask is appropriate. If you want to check the mask is appropriate, I can do that, and oh well, nothing's perfect. No. And just verify that it is actually on the brain. Right, we're losing out on the brainstem, but at least we're covering all the brain, so that's good. Not a bad job. WO2 response on that now, so I just need to do that. Again, that's going to use the outer shell only because, sorry, I've got to put my name in there. Right. Okay. Any other requests while we're here? Oh.
So we noticed that there was some 100% bleeding on the intensity of our data, for example, that if you go to our data, you see that some slices are a bit more intense. I don't know if you noticed that.
I did, yeah. So
how will that affect the
so this is something that you have to worry about. And I have noticed it on the Philips quite a bit. And there's reasons for it which you will be able to confirm for me because you will probably hear it at the acquisition. But definitely you can see this kind of striation pattern here. So on our system, what we've noticed, and it was very clear-cut on neonatal data, is that alternate slices that were the problem. That's due to a 2-second delay between volumes, which you can't disable. If you go dig in the Philips code, okay, which we had to do because we rewrote a lot of the sequences, you will find a one line somewhere that says insert 2-second delay with a comment dating from 1992 about this being to compensate for eddy currents. I don't know why it's still there, but it's there. And that means that now your even slices will have a 2-second gap before anything's happened, but your odd slices will be coming right after the even slices have been played out. So because of crosstalk, the odd slices will have been saturated a little bit more than the even slices before they get excited. All right? So that's the cause of the problem mostly. From your data, I'm guessing you've used the Phillips interleave. I don't know why. It's a weird thing that they have there. It's taken me a very long time to understand what that meant in Phillips speak. On the Siemens, when you talk about interleaving, you're talking about evens and then odds. So I recommend you stick to Phillips default, not interleaved, because that's probably related as well. And in your case, for example, I'm guessing you've got something like 64 slices or something. It'll interleave, it'll come back every 8 slices, it'll come back to the next one. And then that means that you've only got 8 slices worth of gap of time before the next slice, adjacent slice, gets excited, which means the crosstalk between that first slice and the next one has only had maybe a couple of seconds at most to recover. Whereas if you had a full odd and even interleave, it would be more like 5 seconds. So I'd recommend that. Now the problem is, if you do, if you do a tensor fit, you might think, well, we're fine because we're normalizing to the B0, which has exactly the same artifact. But that only applies if you haven't done any regridding. And the minute you push it through eddy, it'll regrid. So all this bleeding will kind of affect the whole lot. So you do have to worry about it. If you can fix it, fix it.
Yeah, so it will, change the direction, just the position to the default one.
Yeah, basically. But you've still got that 2-second delay there. That I don't know how you. There's no way to disable it that I can tell.
You have to go to the code.
Yeah, but you probably hear it when you play the sequence out. It does a 10 seconds of EPI, 2-second gap, 10 seconds of EPI, 2-second gap, and you can't get rid of it. I mean, when I was trying to figure it out why the data that I was getting from King's before I joined King's had this zigzag pattern to it, I actually asked them to sit in the scanner and listen just to check that that's what was going on. And sure enough, there was a problem there. Yeah, okay, so we've got that. Let's have a look at the response. Again, not bad, B2000. You see, it's a little bit, it's not quite as sharp as the B3000, but it's still not bad at all. And we got a mask, we got a response, so we can, run the CSD on that stuff. What was the... Okay. And again, we've automatically selected the B2000. Okay. Oops. So it's looking a bit smooth and whoa. Oh, that's just, okay. That's just so you got a fat artifact here. So you might want to look at your fats at.
Phillips is bad for fat saturation.
You can do quite a lot, but yeah, you've got different modes. So we use a spare pulse. But we've got problems with neonates as well with fat. So we now also put on the gradient reversal. So the gradients are reversed between the 90 and the 180, which means the fat shifts out of slice differently. Yeah, but that's what they use also on the HCP data. But I don't think you can do it without modifying the sequence. But otherwise it looks fine. And so what have we got? Okay, so who can tell me what's wrong with this? Yeah. So one of the grads is pretty is a bit off. So as a coronal acquisition, the coronal slice I'm displaying now. So I would probably invert the Z component, but it's not necessarily the only problem. So let's have a look at it. Hang on, if I can see, if I can find my way here. Where am I? Here's a corpus callosum. Okay, so inverting the Z would be the wrong thing to do because that's looking right. That's the pons, right? That's the brainstem. So in that plane, that's looking like it would be right. If I inverted the Z, that would completely screw up the brainstem. So going back to that coronal view, what I want to do is invert the X. Okay, so this is fun. So I've got these, what are they called? Grads. So at that point, you have to just yeah, have fun. So there's various ways of doing it. I'm going to just do it the old school way because I'm a nerd of the highest order. And print -$1, $2, $3, $4. Okay, let's just check what happens. So you can see I've inverted the Z component, the X component here, so I'm going to put it in my new grad.txt, push. And we're going to redo the, so note, remarkably, the response estimation is okay. It's the subsequent FOD that's problematic, okay? So, there's no need to redo the debride response step. But it's, oops. Thank you for saving my bacon once again. There we go. So these are the kinds of things that you have to massage when you kind of do your own imports, and why I recommend DICOM, if at all possible, because we try and make sure that that's dealt with. But at least that one's an easy one to deal with. What I was also worried about is that, for example, you have a transformation matrix here, that 3x3 part, the first bit here, so that's just the translation part. That first 3x3 here is not the identity, it's not diagonal. That means there's some rotation to the data, and that means that it matters whether I use a BVEX or a grad. And for you, it matters whether you've typed in these manually and where you got the gradient table from. Okay.
The gradient directions are derived using your gen command. And,
so, but you typed them in manually to the scanner?
Yes, we did.
And then the grad.txt file that I just got there, where did that come from?
From exporting in PAREC format.
Okay.
And then deriving the directions from that file.
Just taking them as is. So I'm expecting PAREC will store the directions in scanner coordinates, but I'm not convinced it's true. But
in any case, well, I think they are in scanner coordinates. I will have to check.
yeah, it's worth double checking that. But anyway, so this is a simple trick to invert the X if that's all you need to do. But if it's worth acquiring a really strong oblique to see if that is a problem. Anyway, so let's load up the FODs. And there we go. So this is magically fixed itself. So you see the fat here is really screwing up that part of the image. It's a shame it's going there, but it's just above the anterior commissure. Now, the image is upside down, which is annoying. I wish I could fix that. What can I do to fix that without messing everything else up? Not a great deal. So the problem is that if I inverted the image, which is easy to do, the FODs would still be pointing the wrong way. So it doesn't matter. We'll just leave it as is. It doesn't matter. But you see very much the kind of structures you want to see. So middle cerebellar peduncles and cortical spinal tracts here. So just to get oriented as to what's going on, I find it quite useful to just run a whole brain tracking just to see exactly what we're looking at. Right, and at that point we can probably have a little break or talk about something else, or just generally just, if anybody's got any jokes, I don't know. No, yeah. Mm-hmm.
So I cannot change the.
No, sure, yeah.
So, are there any post-hoc type of pre-processing that we could do to try to minimize that? For the connector, I don't think will be a problem to fit. I mean, because it's just fitting the tensors. But if we want to do like CSD, for example.
So So the first thing is it's not an enormous effect. It's visible, but it's not an enormous effect. The second thing is if you want to do, depends what you want to do. If you just want to do tractography, I don't think it's going to have a massive impact on the tractography because the amplitude of the FODs is only really used to as a cutoff when you track. But otherwise it's just going to sample from that distribution, irrespective of the amplitude of it. Where it might get tricky is for more quantitative comparisons when you want to do pixel-based analyses and SIFT and stuff like that, where it does rely on that being relatively accurate. I'm not aware of any kind of things you can do, particularly.
Normalizing the intensity from the other neighbors.
Well, the thing is, you've got quite a regular structure in your data. So if you, before processing at all, what you could do is just try and apply a correction just by figuring out roughly what kind of intensity scaling you get. The problem is it's not a pure scaling because it will be T1 dependent. And also movement will impact a little bit on that, but then you can't do very much about that anyway. So what you could try is try and figure out if there's a little gradient of values that you can repeat every 8 slices to just scale them and see if that helps.
Right.
But other than that, I'm not sure. No. Yeah. Yeah. It's almost there. So interestingly, you'll notice how many tracks are getting selected out of that's about a 1:2 ratio, which is surprising. So let's hope it's not a big problem. Oh, it's messy. Okay. That is pretty messy. Okay. I've seen cleaner data, I have to say, but I'm trying to figure out why they would have so much. So I think there's a lot of noise here, but that's probably okay. That's the fat, so I'm just going to ignore that. Okay, so the tracking is struggling a bit with the kind of masking, basically. So it would help a great deal to have ACT applied here. But there's also a lot of stuff in the ventricles, so the multi-tissue CSD would do a lot better here, and you have the data for it. What I could try and do is run that now, and then we can talk about something else for a half an hour.
There's another topic coming about this, so if you want.
Oh, sorry.
And then we can talk about it.
I know, I can keep going for years, so just, you know, you have to stop me. Please. Yeah. So if you want to keep going just with something else, let's do it. Let's do it. Let's do it. I'm just going to set this running and then we can have a look at it later. So this is this new algorithm that I have no experience with, so we'll find out. Oh yes, okay. So these will be the output responses. All right. Someone else want to talk?
Okay.
Cool.
Thank you very much, Donald. So, I don't know, somebody, ¿alguna pregunta particular?
This is his last talk, right?
Ya.
Phew.
Después de 4 bondadosas pláticas de Donald, esa es la última, entonces, por supuesto, hay espacio para una pregunta o algo así, pero vamos a seguir conviviendo en la comida, entonces quizás, no sé si no hay ahorita alguna, pero pueden buscar. ¿Vale? ¿Sabes qué será?